Okay, let's discuss constructive and destructive interference in more detail. We have two waves, the blue and the green one here. They are not of the same amplitude, but they have the same wavelength. Since they are traveling in the same medium, we can also infer that they have the same frequency, same wavelength and same frequency. Now, there is an additional property of these two waves. We say that they are in phase. What do we mean by in phase? Two waves are in phase when a crest coincides with a crest and a trough coincides with a trough, like here. Whenever this wave has a crest, this one has a crest, and vice versa. The wave obtained when we have these two waves meeting at the same location is what we see here. We have constructive interference as at any point of this wave, the amplitude is obtained by adding the amplitude of the amplitudes of the blue and the green waves. For example, here, the amplitude of the crest is going to be the amplitude of this crest plus the amplitude of this crest. The amplitude of the trough is going to be equal to the amplitude of the blue trough plus the amplitude of the green trough. Any point, the amplitude at this point is equal to the amplitude of the green one plus the amplitude of the blue one. So this is constructive interference. Let's look at this other example where we have also two waves that have the same wavelength. In this case, they also have the same amplitude. But these waves are out of phase. Notice that the crest coincides with a trough. That's when they are out of phase. Whenever a crest coincides with a trough, we say that the waves are out of phase. When these two waves meet, the amplitude, very much like what we had here, the amplitude of the resultant wave should be the sum of both amplitudes, the amplitude of this one plus the amplitude of this one. Since this one is a crest, positive amplitude, and this one is a trough, negative amplitude, they add up to 0. And that's why we see nothing here. And that's the same thing for every point on those two waves because the waves are identical. Let's examine this in an animated format. In this video, when we run it, we have these highlighted dots that will show us the behavior of the waves. The waves are going to be moving or traveling towards the right, the blue one and the green one, and you'll see the behavior of these indicators. The amplitude of the resultant wave is going to be equal to the amplitude of the green one plus the amplitude of the blue one. You notice that this one is this plus this. Now we have destructive interference. The waves are moving again towards the right, but in here we have the crest coinciding with the trough, and they are of the same amplitude. So you see the amplitude of this one is equal to the amplitude of this one and this one, but this is negative, this is positive, so they add up to 0, or vice versa. Okay, let's examine what happens when the waves are not identical. So we have the green wave. We have another wave, and you notice it's a different wavelength. We see now both of them, and we see the sum. Let me pause it. Notice here, the sum for the red one is going to be, the red one, which is the sum, is going to be green plus blue. That's what you get here. Now, at any point, for example here, The amplitude of the red one is going to be this plus this. Notice that the red one is not a sine function anymore. It's more intricate because these two waves are of different frequencies. And that's what we see. Okay, we are showing it there by itself, and you notice how it is actually a more complex waveform.